My name is Hubert and this is Teach Me channel. Today we will look at how to solve energy store equations. So, if you are not confident about what energy stores are and what types of energy stores there are and how we can transfer that energy, check out the video in a link in description below. That will help you immensely for this video. So, without further ado, let's get on with it. So, first of all, we have gravitational potential energy. We need to know how to calculate the gravitational potential energy stores. Okay, so this is, long story short, this is the equation that shows us how much gravitational potential energy we have stored. So what does this equation look like? Here we have gravitational potential energy. Here we have mass of an object in question. Here we have gravitational field strength. And here we have height. Now, this equation logically makes sense, doesn't it? Because when you look at it, if we increase the mass of an object, it is harder to push it up the hill. It is harder to store that gravitational potential energy. It is harder to push it up the hill. And therefore, we need to transfer more energy into it. So we need to convert more energy into gravitational potential energy. So if the object has a higher mass, then for the same gravitational field strength and for the same height, the object will have higher gravitational potential energy. Now, gravitational field strength is important because on Earth it will stay constant. However, if we did the same on a different planet, for example Jupiter or Moon, Jupiter would have much higher gravitational field strength and Moon would have much lower gravitational field strength. So for example on Jupiter, the gravity would be pulling that object downwards much harder. So same concept here. We have to put in much more energy in order to push that object upwards, and therefore we have to convert much more energy. So we will be converting much more energy into gravitational potential energy. With height, if we gotta push an object higher up, then of course we need to put in more energy in order to push that object higher. Therefore, we are converting more energy into gravitational potential energy. So with the bigger height, we get bigger gravitational potential energy. And conversely, the higher the object goes, the harder it falls. So the saying goes. Because if we push the object higher, then we get more gravitational potential energy. And then we convert more gravitational potential energy into kinetic energy as we drop the object. Now, this is the next important concept. Gravitational potential energy loss is equal to kinetic gain. So gravitational potential energy loss is equal to kinetic energy store gain. And converse is true, where gravitational potential energy gain is equal to kinetic energy stores loss. Now, if we think about it, it makes sense. So, for example, let's take our previous example from previous video, where we have a guy standing at the top of a cliff with a freakishly large arm and dropping a ball down the cliff for no reasons, because it's physics. So he is dropping a ball down a cliff. So what happens here is that as he drops it, gravitational potential energy gets converted into kinetic energy. So that's where this relationship starts coming in. Because as the ball loses gravitational potential energy, it gains kinetic energy. Now, opposite example is true as well. here we have a roller coaster track. So essentially we have a hill, and the roller coaster is moving up the track. The roller coaster is moving upwards. Therefore, it is converting kinetic energy that comes from its motor. It's converting the kinetic energy into gravitational potential energy. It's putting in that kinetic energy to get gravitational potential energy. So again, if it moves to the top of the hill, it gained gravitational potential energy, however much kinetic energy stores it has lost. So this is a useful relationship to use in questions. Now, so this is it for gravitational potential energy. And now let's move on to kinetic energy. One sec. There we go. So here we go. Here we have kinetic energy. This is our equation for kinetic energy. However, before we go into that, we need to think about what is stored kinetic energy. How can we store kinetic energy? I mean, after all, when we move a car, we need to keep putting petrol in. The motor needs to keep working, otherwise the car will stop. So how on earth is that car storing kinetic energy? Well, in order to explain that, let's think about a different scenario. Let's think about a ball. Actually I will add a hand here. My artistic impression of a hand. Okay, so we throw a ball in a space. What are we doing? We are transferring kinetic energy from our hand onto the ball. Now, because it is in space, there is no friction, there is no air, there is no atmosphere, there is no friction or drag that will stop the ball. So the ball will continue traveling at the same constant speed forever and ever until something acts on it. So, in other words, the ball is storing that kinetic energy that we transferred onto it. The ball is storing that energy because it's traveling forever at the constant speed. So that is how we can understand storing of kinetic energy. Now, this equation will make things even clearer for us, because kinetic energy storage is equal to half the mass multiplied by velocity squared. Now, velocity essentially, as far as you're concerned, it means speed. It is not exactly the same as speed, but at this level, as far as you're concerned, it means speed. So, let's have a think about it. If we have a higher mass, again, same concept as before. If we have a higher mass, it is harder to move that object. We need to transfer more energy onto it for it to be able to travel at the same speed. Therefore, we are storing more kinetic energy in that object. And the similar things goes for speed. If we want to give that object higher speed, well, we need to give it more energy. We need to transfer more kinetic energy onto it. So if we transfer more kinetic energy onto it, it ends up storing more kinetic energy for us. Now, in this case, units are very, very important, because in exam they will try to catch you out with units. So energy is store energy. The standard unit for energy is joules. Standard unit for mass is kilograms. And the standard unit for speed is actually meters per second. Here, that's where they might try to catch you out. I will mark this for you. There we go. So, here, they might try to catch you out by telling you the speed of a car in kilometers per second, in which case you would have to convert it back down to meters per second. However, okay, so concept-wise, this is it for kinetic energy. Now let's look at the final type of energy we will discuss today. 1 second. There we go. Okay, so this is elastic potential energy. As we talked before, elastic potential energy is energy that we store when we stretch something, be it a spring or a rubber band. If we stretch it, if we hold it stretched, we store that energy, and when we release it, and as the spring snaps back to its original shape, it releases the elastic potential energy. Now, let's have a look at the equation. Elastic potential energy store is equal to half the spring constant times extension squared. Okay, so what does spring constant mean? Spring constant means, essentially, a good way to think about it is how hard the spring or the rubber band or the object is to stretch. The higher the spring constant, the harder the spring, the object, is to stretch. Why does this make sense? Well, if we have let's say we have a easy to stretch spring, for example a spring in a pen, and let's have a hard spring to stretch, for example a car suspension spring. Now, if we put the same amount of energy into each of these springs, then we will stretch this one by much less than we will stretch this one, right? So let's think about it the other way around. If we stretch the spring to the same extension, to the same amount of extension, if we stretch each spring by 2 centimeters, for example, then we will put much more energy in stretching this one. If you think about it, you would really have to struggle to stretch this one with your bare hands. Whereas we put much less energy here, because it's fairly easy to stretch a pen spring. Now, this is made clear in this equation, because if we increase the spring constant while keeping extension the same, basically the scenario I just described, then we will increase the elastic potential energy stored. We will transfer much more energy into the hard to stretch spring than we would to easy to stretch spring if we had the same extension. Now, another concept we need to talk about is extension here. Well, if we extend the spring more, we clearly need to put more energy in. Therefore, it makes sense how increasing the extension will increase the elastic potential energy stores. And the final concept, actually, we need to cover here something. We need to cover units. So, in elastic potential energy store, we express that in joules. Again, standard energy unit. Now, what do we express extension in? We express extension in, again, standard unit, meters. Now, spring constant is expressed in newtons per meter. That makes sense, doesn't it? In newtons that you need to apply, newtons is a unit of force, the force you need to apply to stretch the spring by meter. So here we have newtons per meter. Now, so that basically describes the equation, and the final concept we need to talk about in elastic potential energy is the limit of proportionality. Well, if we say, for example, we take the pen spring, if we stretch it too much, if we stretch it way too much, then it will not return to its original shape. It will not return to its original shape. Therefore, it will not release all of that energy that we stored in it. in a way we can predict. It becomes much more unpredictable what happens here. So this equation can no longer be applied if the spring has exceeded its limit of proportionality. We can only apply this equation when the spring or rubber band or whatever we are stretching stays within its limit of proportionality. Okay, so this is it concept-wise for today. However, we need to cover one more thing. I prepared something for you guys. I prepared a question. It's a quite challenging question at this stage. So I will tell you about this question first. A rocket with mass of 10 kilograms is shot directly upwards. It travels at a constant speed of 20 meters per second. It eventually comes to its highest point and stops. And this is a two-part question. First part is asking you how much kinetic energy has the rocket stored, and then second part of the question is asking you how high did the rocket go. Here I gave you a little summary diagram, the 10 kilogram rocket, and I gave you the value because this question assumes that we are on planet Earth at this stage. The gravity field strength is 9.81 newtons per second. So the rest of it, I leave it up to you guys. I'm really interested to see what you guys come up with, so please, if you know the answer, or if you even want to just tell me how you're thinking about it, just give me a comment below and we can have a nice discussion about it. And if you're interested in science videos, daily science videos and daily maths videos, as well as some university level biomedical sciences, smash that subscribe button below. If you like this video, give me a thumbs up. Thank you very much for listening. I really appreciate you guys. Thank you very much, and see you next time.